Yes. I need to make a brief announcement. If we have anybody who wants to join the excursion but did not register, right, we still have open seats. Yeah, if you want to join, or if you have your partner with you, yeah, who is not registered at the conference, right, we still have seats in the bus available for the very nice tour we do on Friday afternoon. Just let Dennis know, or let me know, and then you show up at 1 p.m. on Friday in front of the local. Thank you. And the speakers, if they would send a PDF of the presentation to send me so that we can put it online. Right? Thank you.
Okay. So welcome back to our second part of the session on scalable cloud data management. In the morning we have heard the view and some issues from Hamburg, and now we will have Heiko here and later on Uta to round this up and give us some more insights. Let me also tell you that this session is somehow has been compiled according to your participation in that workshop that Norbert was mentioning, that workshop on scalable cloud data management. And so we also get part of that workshop by having your presentation and your presentation. So Heiko, please start.
Thank you, Leonard. Thank you very much for the invitation to this event. It's a pity that I didn't know about this beautiful place and this interesting conference before. So I'll present Polypheny-DB, which was mentioned before. Many thanks to Norbert and Felix for their great presentations, which have paved the way already, and which means that I don't need to introduce all the basic notions. Polypheny is a strange title. It is derived from a concept from genetics, polyphenism, which means that that different phenotypes can arise from a single genotype on the basis of environmental influences. And it should, to some extent, highlight the adaptivity we will take a look at later on of Polypheny. Before I go into detail, just a quick Geography 101, because Bernard mentioned this to be, or introduced this to be a German session. So it was the University of Basel, and if you zoom in, there's quite a difference. And Basel is close to Germany, but it's still
Quite where you put it.
below the...
I would have put it somewhere else.
Yes.
Yeah, it's not properly.
So it's now in a Dreieck.
Yeah.
But since the Swiss gave me a Swiss passport a couple of years ago, I need to...
I have a Swiss passport.
Yeah. So I went through the Swiss makers process. And one more slide before I go into details of Polypheny. Let me quickly give a brief overview on the activities of my research group, because this might be relevant later on. So we do traditional database stuff, distributed data management. We do data stream processing. So to I thought if I get impressed by the presentation, you will keep the so we do some...
Do it again.
We do data stream processing, but we also do very strange stuff for a database group, which is dealing with unstructured data. We have quite some activities in multimedia retrieval. And actually the work on Polypheny-DB, Polystore work, is the glue that brings all these things together. So, but I will focus on the cloud data management part, or distributed data management. And I'd like to start with a brief scenario to motivate with you. Let's assume we have an auction house, and the auction house operates globally, runs billions of auctions a day, has servers deployed around the globe, and there are quite some requirements. Of course, data availability is important. You don't want to lose customers because data is not available. Performance and latency is a very important issue, especially if auctions come close to the end. There might be different query types, we'll take a look at this later on, and some other aspects, and of course I did my homework yesterday as well. GDPR compliance, privacy is of course very let's take a look at the different query types such a scenario should be able to cover. Well, first of all, there's the traditional OLAP. This should be OLTP. Traditional OLTP workload. So relational data model, SQL queries. There should be a recommender system, so people who have placed bids for one item also placed bids for related items, or it usually comes with a graph data model and queries on the graph data model. Analytics is important as well, okay? And the auction house may also support some kind of similarity search. So I was at an auction recently and I saw this nice painting which destroyed itself. Are there any other artifacts and items available in an auction that look similar to the one I took a photo of before it destroyed itself? So it is similarity search on multimedia objects, which means that we have to deal with high-dimensional feature vectors and vector-space retrieval, unstructured data, completely different requirements. And of course, one approach to address this has been introduced much nicer by Felix and Norbert before, is to use specialized systems, so to keep a slew of systems, one for each particular challenge, which is complex to set up and maintain. In particular, it's difficult to optimize automatically which data goes where, and if data is replicated across different systems without some central coordination, it is difficult to keep data consistent. So the Polystore, or Multistore, in our case it's a Polystore approach, is not just to have one system, but to have one entry point into a system that is composed of specialized systems, with the objective to have a better resource optimization, to have a more generic approach, and to be able to better optimize everything that is underneath the Polystore interface. So as Felix mentioned, the one-size-fits-all approach certainly doesn't help, but the Polystore has the objective to at least mimic the one-size-fits-all. So the objective will be to have good performance for mixed workloads, OLTP, OLAP, graph queries, unstructured queries on unstructured data, offer different data stores, different data models, maybe even storage technologies to trade off latency versus price. When you have main memory databases or solid-state disks or hard disks. We also want to support multimedia retrieval, so deal with unstructured data. And then, of course, the objective is the optimization, to automatically optimize queries by selecting the best data models, the best sites in a system. And we want to scale this to the cloud. So ideally, we will be able to distribute the Polystore functionality to the cloud, and finally to adapt to different workloads. And the big picture of Polypheny-DB is to have, as a logical view, one large database system, which at the end of the day is distributed, for instance, in the cloud across different regions, in different availability zones. And one challenge is the distribution of data across regions and availability zones. And then if we take a closer look at the different availability zones, the Polystore concepts come into play. That different data stores, different data models, depending on the type of data, depending on the concrete requirements, are locally deployed. So this is the big picture, which means that there are two challenges to be addressed. One is the global perspective, the distribution of data across different sites, and also the adaptation of data distribution And on the local perspective, the selection of data models and the decision which data goes into which data store. So that's why I will first take a look at Polypheny-DB in large, so to address the distribution aspects, and later on Polypheny-DB in the small will be the Polystore aspects. In the large means that we have data, we have a distributed system, we need to find a way to place data on sites in our distributed system, which means that we need to address fragmentation, so how to split data properly, ideally to the workload to collocate data items that are frequently accessed together. Data replication is very important to be able to guarantee high degree of availability. We need to have several replicas. Data allocation, what data or where to put data, and finally migration, because this is not a static thing, but should be dynamically updated with changing workloads. Let's go through all these four aspects. So fragmentation is clear. The objective is to have some load balancing. So ideally to be able to parallelize queries, so data should be fragmented, especially if data are unrelated, not jointly accessed in the same transactions. Also because of horizontal scaling. So this could be horizontally or vertically, and the idea is to come up with a fragmentation model that takes into account as input the current database schema, metadata, and in particular the transaction workload, and that tries to model the entire database as a graph and split the graph into partitions so that the subgraphs are more or less consistent with regard to the transaction workload.
Is this what the human being would have to do, Heiko? This modeling?
Ideally, this is done automatically.
That's one. Okay, thank you.
Yeah. So the model is, and there's an example of things we've concretely addressed exactly in this case. So this is a workload-driven adaptive partitioning model and a protocol, in particular for one-copy serializability executions, so with strong consistency. And this takes into account costs that occur for guaranteeing consistency, for instance, the cost incurring for messaging in a two-phase commit coordination, takes into account costs for availability and a couple of other cost parameters, in particular the current workload. And the idea is to come up with a partitioning to identify which tuples are frequently accessed together. And again, this is done by converting the content of the database into a graph and by identifying which tuples are jointly addressed. Replication, second requirement from a global perspective, is important for availability, also for load balancing, but it comes with the well-known constraints regarding consistency. So in case of failures, the CAP theorem will be needs to be considered in normal operation. There is a trade-off between latency and consistency. So the question is whether to enforce latency or whether to enforce consistency. So there are a couple of approaches that either support either high latency or a strong level of consistency. And again, the idea is to come up with a replication model that takes into account the fragments. So the result of the previous step of the data fragmentation, again, workloads, possibly policies, privacy area, which data might be where. And the idea is, the objective is to determine the replication factor, how many replicas do we need, and in particular the replication protocol. How do we coordinate updates to these replicas? And again, we have two very concrete contributions. In this case, one is called C3. C3 is a protocol that automatically switches between different consistency levels on a cost-based approach. It takes into account inconsistency costs. Inconsistency costs, for instance, that occur if you produce inconsistencies. So if a bookstore sells books that are not on stock, and then the idea is to have some kind of application-specific notion for the consequences are that either customers are lost or they need to be compensated. And the inconsistency costs are compared to the costs you need to invest to guarantee a certain consistency level. So for instance, this two-phase commitment.
What does it mean, the dynamically? Every other community changes the model, or?
Well, ideally, if the costs differ so significantly, yes. Usually, it is not something that changes so frequently. So let's come back to the bookstore example. If you have 200 items of book in stock, you don't worry about consistency. But if you're close to getting sold out, then it might make sense to switch to strong consistency to avoid that you have inconsistencies. And the idea is to calculate the expected costs for one conditionalizability, to compare these costs with eventual consistency, and depending on that, determine the protocol to be considered. Another concrete example we did was the consideration of the commit path. Again, in a one-copy serializability approach, the idea is not necessarily to include all sites in the eager update commit, but just some in a quorum. And then the challenge is to find the best sites that should be integrated into this quorum, depending on, for instance, the load of the sites, the round trip time. And this is also something that decided dynamically based on the actual load and on the costs that incur. Of course, there's also something that can dynamically change, and if you have sites that are on site, the right quorum, in this case there is none, but if there are sites on site, the right quorum, then of course if you change to another right quorum, you need to update these sites first. But again, the idea is to do it automatically on the basis of the cost model. Allocation, the third of the four building blocks. The objective is to allocate the fragments and the replicas to sites, again, by taking into account the load of sites, network properties, round trip time, and to assign fragments to nodes. And last but not least, the last step is the migration. If the allocation changes, then of course data needs to be migrated, either in offline mode, so to stop the entire business, start the migration, or to do this online, and migrate data in the background, which has then severe consequences also on the replication and the consistency protocols that are deployed. So the first model is the migration model that takes into account current workload, again, network properties, that assesses the cost that incur for migration versus the gain you will have when migrating the data. And the output is to select dynamically the migration model and the method to consider. So all four items together, of course, need to be combined in order to have an adaptive system at the global level. So to do the fragmentation first, once you have identified your fragments, to address the question how many replicas per fragment are needed, where to allocate them, and when and how to migrate. And of course, these four models for this need to be combined in a joint cost model.
And what kind of cost do you have? So the question, if I do a cost-based query optimization, I need to run statistics to find out how the data is distributed. Do I have to do the same here too?
Yes, in some cases these costs are static. So if you have, for instance,
I understood that. Yeah.
and for the other, of course, you need to do statistics, and you need to combine the static cost items with the dynamic ones.
And if the out-of-the-box database doesn't do it, like MongoDB, I don't know, then are you doing that?
Yes.
Oh, okay.
So the idea is to do this one level on top.
Okay.
So Felix mentioned before, Polypheny-DB does not exist. Well, yes, this is true. It doesn't exist as a system to download and deploy. But several bits and pieces already exist, especially in terms of fragmentation, replication, and allocation, and we're currently working in gluing together all these bits and pieces. And again, the idea is, once we have this joint cost model, to consider fragmentation, replication, allocation, and then migration in a joint cost model to assess the costs, also assess the potential gain, and then finally make a selection that the best candidate is selected so that the decision to eventually migrate or change one of the underlying protocols is then derived out of this process, and the new state will be created. So this is something that will be done continuously. And there are a couple of challenges we are currently facing. We like to have everything as modular as possible. So to ideally be able to add new protocols and integrate new protocols into these host models, that they're new protocol for consistency, DDN plus first conventional consistency when it comes in, that they might be able to use this. And of course, all these bits and pieces are not completely independent, so currently you're facing the challenges how to deal with these influences and dependencies between the different ones. Also the question is when to adopt, what time frame to consider, how to avoid cyclic migrations, what is a good time frame to consider for changes, how stable should the system be, how should the thresholds be defined, could they be learned. So these are current topics here. So this is Polypheny-DB in the large. Polypheny-DB in the small means that internally on each of the side, once we have decided which data to store where, the question is which data model to use, which data store to use to store data internally. And this is very close to all the challenges Norbert and Felix have already presented. Some data stores are better suited for specific scenarios than others. Even the same data stores could have completely different properties when considering the storage technology underneath. So the disks are slower but cheaper compared to main memory. So depending on whether cost or latency is an option, even inside the same data store, the physical layout can be different. Another question is again the same problem we have already faced at global level. So now we have a fragment of the entire data set to be stored locally. We have different data stores. Do we store all the data in the data stores? Do we fragment, possibly also replicate, where to allocate the data? So again, the same questions in the small arise. and it makes a big difference if each data item is stored just in one local store or in several stores, because then again you have to deal with consistency at the local level.
Sorry, that means different copies of each data. In the first, in all stores, each store contains a copy of the data. Is that true?
Yeah. So if we have one node, let's take this one here. There is a fragment of the entire data set to be stored on that node, and we have several stores on this node.
And in each store you have a copy of that data.
Either or, we again fragment the data and decide where to store which fragment internally.
Okay.
And this, we'll see a concrete example later on. This depends also on the nature of the data and also the nature of the queries. In some cases it makes sense to store each data item on each store. In some cases it makes more sense to fragment. And ideally, the same properties we have at local level as well. There's the dynamic placement, the dynamic fragmentation, the dynamic migration, and all the dynamic adaptations we have at global level, also small at the level of the individual sites.
Can't it be that the local optimization interferes with the global one, and that the global one needs to override it and so on?
Yeah, this is a very good question. This is one of the problems we have in structure because of all the interdependence. Not yet. So this is something we try to work on to at least come to some heuristics on how to weigh the global optimization versus the local.
I recall when I still was the IBM had this autonomic manager, it was a hierarchy, and they were fighting with each other. The system was oscillating and so on.
This is what we want to avoid, but we don't have a solution to this. This is what we want to avoid, of course, the oscillating behavior, but we do not yet have a good solution. At the end of the day, I guess we need to be some kind of pragmatic. Query interfaces. Well, Polypheny-DB on purpose declared itself Polystore, and Felix made a good introduction into the terminology distinction between polystores and multi-stores. So on purpose, we want to have several different query languages at the interface. We have several SQL dialects we already support. We have a Crete interface, OpenCipher, so graph queries. We have not yet implemented, but we've had support for vector space retrieval for similarities.
So for each of the underlying stores, you use the existing APIs. Is that what you're saying?
Yes. But this is what the Polystore on top of the underlying stores exposes to the outside. And this is then mapped to the APIs of the underlying stores.
Crete query language is just create, update, delete.
Yes, very simple.
So the word query language is a little bit. You just made it because it fits in the picture.
You can put it in quotes.
Yeah.
No, it's okay.
Let me put it in quotes. So we have it in quotes. What we plan to do as well, this is not yet implemented, is also to go into multi-version data management or temporal aspects, especially in the case of replicated data. This would allow us not to synchronously update all replicas, but on purpose to keep several replicas out of date, to have different levels of freshness, so that we can trade data freshness for latency. So this is something which is on our agenda, which is not yet. And of course, self-activity also addresses the lower level. So we need to constantly change the configuration whenever the workload significantly changes, both in the large and in the small, both in terms of the distribution of data and the storage of data on the local data set.
So question.
Yep.
On the figure it says 4 things to know about adaptation. But you only have 3 marks on the left side. So what is the 4?
So the author of the URL was
Maybe.
was confusing.
This is a good point. I didn't pay attention to it. So this is eventual consistency. You might take a look at it and update it. So coming back to the big picture, we need at runtime, of course, to address the data distribution, and this is done both at a local and a global level. And at query time, we need to select first the proper sites to execute a query, and then inside the sites to select the data stores where we want to retrieve the data. And since this has all been very abstract, let's take a closer look to a concrete example, multimedia.
Go back to that slide. Do you have any idea how to manage transactions on all of them? Just recognizing that all this is even the possibilities of commit coordination or the isolation are so different. It is so much a challenge to bring all that together. But do you have at the interface an idea of what notion of transaction you want to give to the application?
The idea is to again decide.
Maybe you all talk a little bit louder.
Okay.
Yeah, I can hear it, but I'm pretty sure that over there.
Now that asks how to implement transactions in this big picture.
And what is the transaction model?
Yeah.
Yep. And the idea is to again decide on this dynamically on the cost aspects. So I have shown the DC3 approach before, which was quite successful in the small. To decide on the transaction model, on the consistency level, based on the different costs that incur on the local scale. If we have one site with several systems where data is replicated, to take into account the different costs that incur. And our objective is to promote this to the global level as well.
Heiko, when you end up with a data mess with the database. So I do asset transactions in 1 minute, and then compensation-based recovery 2 minutes later, and then the asset again. You don't know what the state of the database is, isn't it? I'm serious, I'm asking.
No, but if this is a good point, but if this is important, this should be reflected to some extent in the cost.
And the cost
then you avoid this mess.
Yes. Yeah, okay.
But if really the mess is okay, which means that you're not worried about inconsistencies, you can create this mess, and if your concerns are that data should be consistent, this should be part of the cost.
The answer is correct, but I hate it.
But you should also tell us whether the queries only go down or whether you can have queries that go horizontally. Can you query everything? Or is it that you just find the right, let's say, store, and then you go there and you get what you need?
Can be horizontally as well to guarantee for horizontal scalability. If you do not replicate the data but just partition it, this means that the global decision would be not just select one region, but several or even all regions. This again depends on these decisions on how data is distributed. Further questions?
When it is handled by the cost model itself, isn't it just a shift to the cost model how to configure the system in the end in order to make it reasonable for this particular application? So then you have to configure the system, or you're shifting the problem related to the cost model. This is what I see support.
Yes. In addition to have one static decision, the idea is to delegate this to the cost model with the option to at least dynamically adjust if this pays off. Like if you have to in the traditional case where the system administrator takes a look at statistics and reconfigures the system.
Could become a very huge and complex cost function.
10 more minutes.
Let's take a look at a concrete example, multimedia data. What does multimedia data, access to multimedia data mean? Well, over the last couple of decades, when you dealt with multimedia data and you wanted to retrieve data from multimedia collections, it was basically text search applied to multimedia. So let's assume you have a large database with your photos taken from nice places like this, and you want to query, well, what did I do 2 years ago when I was in this conference? Then the keyword search approach means you specify a keyword to search for a multimedia object, and this only works if you have annotated your collection, which usually nobody does. A few years ago, so-called query by example became popular when Google came up with the image search. You can provide an image. So this is my query interest. I'm looking for images that are similar to them, without taking a look at semantics. So the system returns whatever is visually similar to your query. And this has quite some challenges on the underlying system, because what you need to do is to have some kind of feature representation of your object, either by color, by shapes, or by a combination of these, or textures, or whatsoever, which ends up in a high-dimensional feature vector for each object. And similarity search at the end of the day means that each object in the database is mapped to the feature space. The query is mapped to the feature space as well. And similarity search means that you are looking for the nearest neighbors in the high-dimensional feature space, which has completely different characteristics compared to a traditional Boolean database. So we decided to not only start with query by example, we have implemented an approach which is called query by sketch, because query by example is a strange concept. You will never submit a complete website to Google if you're looking for a website, or a complete PDF if you're looking for a PDF. You take the most characteristic elements, and that's why we decided to go for query. Sketches of an object and to search for this. We even extended this. We also saw that when searching in videos, motion might be interesting, so to specify to some extent motion. For instance, in a sports scenario, in the football video, there was an interaction between players that started here and there. The idea would be to automatically select snippets of sports videos with this motion pattern, which we, by the way, did, and it's a very fun approach. Query by concept, to use recent results of machine learning to automatically annotate objects. Query by semantic sketch, which is just a combination of the query by sketch work we did with semantics by drawing a very raw sketch and associating concepts to parts of the sketch. And there's query by time and space. And we've taken all this into consideration, and even a combination of all these ones.
And this is what you already did?
Yes, we did this already. Yeah. And maybe just 1 or 2 more slides on the machine learning stuff. So there is impressive work from the machine learning community on automatically annotating images. So this is what current state-of-the-art deep learning approaches do. They are trained with a couple of images and manually created annotations, and once the network is learned, this is what the network spits out as captions, for instance. And this is what you see in the presentation from the machine learning guys. We took a closer look at the collections they worked with, the neural networks they worked with. We found out that maybe there are some cases where it doesn't work as nicely so the same network, the same collection, but usually you don't find these examples. But coming back to the Polystore aspects, we are now in two different worlds. We have the database community, we have the information retrieval community, and very sadly, there is little overlap between those communities. One community only works with structured data, the other one with structured and unstructured data. Queries are completely different, the interaction is different, the results are different. So we have the structured data on the left-hand side, the unstructured data on the right-hand side. But the question is not, do we need databases or retrieval, but actually databases and retrieval at the same time. For instance, to support queries like, I'm looking for an object that is similar to the sketch I have here, and the painter should be on top. So this means that ideally, some multimedia data management is able to take a query and split the query into different parts. To have the Boolean part, the structured data, and the similarity query on the information retrieval system in the vector space. So this is a bit cryptic, but this means that for this query, color features should be taken. This is the representation of the color features of the sample objects. We're looking for the two nearest neighbors and using the R2 node for the distance in the feature space. And this is what we ended up with by taking a closer look at the different challenges and the different requirements from the different parts of the query. We have the logical view on the left-hand side, where we have different items with structured information, with unstructured information, with metadata. So color feature, this is not a blob, but this is the high-dimensional feature vector. And we came up with a solution, a Polystore, where the structured part goes into a relational database. The high-dimensional feature vectors go into a main memory database, because for information retrieval it is important to efficiently access these, and a key value stored for the actual content. And in terms of the distribution, if you take a look at current collections, like for instance, a sample collection from Yahoo with 100 million multimedia objects, certainly this only scales if you're able to fragment the data, distribute the data, so therefore the scalability, which is the Polystore in the large approach to distribute this across different sites. And last but not least, we have also taken a look at different index structures. So how could index support in a Polystore look like? And in the multimedia retrieval area, there are certain index structures. Some of them are exact, so they rather take long to compute, but return exact results. Some others are approximate, like spectral hashing and locality-sensitive hashing and others, which provide very quick results, but with false positives. And we were wondering how to approach this, and we decided, since we anyways fragment our data, distribute our data, let's try to use as many index structures as possible. We wanted to avoid the traditional kind of request-response query, and we have implemented what we call progressive execution, where we try to come up first with approximate query results, which are being refined once the slower but more precise index structures return the results.
But you already do return at the very beginning data to the user?
Yes. And you see this in the query interface that the results that came first are usually from lower dimensional features and approximate results. They quickly disappear once the new results come in. So users have to get used to this kind of query results that show up, but then again disappear because more precise results come in. So, in this interest of time, I'd like to conclude with summarizing that Polypheny-DB is still in between the vision and the concrete system. A couple of things we already implemented. There are certain challenges ahead of us. The objective is to have the dynamics at the different levels, local and global level, to dynamically adapt and to use different data models, different data stores, different capabilities of the underlying system to combine in a very smart way. And one of the main challenges, as you pointed out, Frank, before, is the interaction between the optimization and the adaptation in the large and in the small interdependencies between these levels. And I'd like to conclude by thanking the members of the DBIS group that have contributed to that. Ilya Fetai, he was the one who has implemented the different protocols for data distribution, partition and replication at global level. Ivan Shankreco is the one who has worked on multimedia retrieval. Alexander Stiemann, the PhD students currently working in this project. And if you're interested in the multimedia retrieval activities, we have a system which is called the Retriever that has participated to several multimedia retrieval competitions and has recently won quite some of them. It is available completely open source and can be downloaded. It's a multimedia retrieval system supporting images, videos, 3D, and video. So feel free to use it.
Music?
Audio, yeah.
Audio is not because of
feel free to use it and let us know whenever you have any interesting ideas on what kind of functionality you want to. So thank you very much for your attention. And
so again, let's use the time when we switch presentations for questions. A lot to research, a lot to work. Yeah, okay. So there's no question. So thank you again. And let's move to the next talk. The next talk is by Uta Störl from Darmstadt, and she will tell us